Hi, welcome to my presentation, a SQL Server programming tutorial, Introduction to Common Table Expressions. So quick check, have you heard of CTEs before? Have you used CTEs? And if you answer yes, great, stick with this video and we'll take a look at some more ways to use them. Have you used recursive CTEs? That's one of the really powerful things you can do with common table expressions is do recursive calls, and we'll take a look at how to do that. And do you use CTEs every day? It seems like I do, because once I've mastered CTEs, it really seems like every query I work on that starts to get complicated, it makes sense to use a common table expression rather than just more and more complicated spaghetti code. So if you're planning on taking the Microsoft SQL Server certification exams, there's usually a few questions in there about common table expressions and how they work. I remember when I took the SQL, I think it was the 70-461 exam, one of the very first questions I got was about common table expressions, and I was really glad that I knew what I was doing with those because it started off on the right foot. So we're going to take a look at some of the benefits coming your way from this presentation. We're going to take a look at what memory tables, this concept of memory tables and how CTE relates to those, simple CTEs, sort of getting started aspect of common table expressions, how to use a common table expression instead of a derived table. This is really great to make your code more readable. How to use multiple CTEs in a query, doing data paging with CTEs, using CTEs in stored procedures, functions, and views. Then we're going to dive into recursive CTEs. But let's get started with sort of an introduction to this concept of what I called memory tables and common table expressions. Think of memory tables as sort of the concept of a derived table or a subquery, where what you have is not a table that you're referencing, but you're referencing another subquery inside of a query. And what that means is that SQL Server sort of treats that as the rest of the query like it's a table, but it's really not a table, it's just a subset of data coming from a query. We also have the concept of views, which is where you can define a query and store that off as something that can get referenced later. And with a view, you have to have special permissions to be able to create and alter the schema of your database. So when you create a view, anybody can use it, well, with the right permissions, of course, but you do have to have extra permissions to create that. And then when you reference a view, you reference it just like a table name. Now, temporary named result sets. There's a couple of ways of doing this. One is to use a temporary table. Another is to use table variables. And we can get into a whole nother conversation on another day about the performance implications between those. But really, what these are is a way to grab some data out of the database and throw them into a temporary place so that they can be reused. Now, a lot of people ask me, well, is a common table expression a replacement for temp tables? Well, sometimes it's a really great replacement for temp tables or table variables, but it doesn't completely replace them. Think of them as different tools in your toolbox. And for instance, just because you have a hammer, it doesn't necessarily mean that it'll do the job of a screwdriver. And I think that CTEs and temp tables kind of work hand in hand really well together in the right scenario. Common table expressions are another way of kind of visualizing or representing the data that's back from a result set in kind of a memory representation where you're accessing and getting at the data from that query. A CTE is kind of this concept of what we're calling a virtual table, where it's like a subquery or like a view, where it's referencing another chunk of SQL query that's going to be used and named, similar to the ease of using a temp table. And I'm kind of using a lot of sort ofs and kind of likes here because it's sort of like a derived table, but it behaves a little bit differently. Say maybe behaves is not the right word. It's coded a little bit differently when you're using it. And it's kind of like a temporary named result set. If there was a concept of being able to create a temporary view or a runtime view, that's kind of how a CTE works. So common table expressions have been available since SQL Server 2005, and I really wish that I'd learned about common table expressions when they first came out. I think it was around 2010, 2011 that I first learned about them, and I think in 2012 was the very first time I gave this presentation at a SQL Saturday event. Common table expressions are available on all versions of SQL Server from 2005 on, including Azure SQL databases. Why would you use common table expressions? I mean, you may have been writing SQL queries for 10 or more years and have never used a common table expression and been able to do everything you need to do. Well, one way is to simplify your query or test one part at a time. I mean, if you ever looked at a query that was 8 pages long in your editor with a 6-point font, well, those kind of queries are really hard to follow, and oftentimes when they've got lots and lots of subqueries in them, they could be broken up and done differently, done as a common table expression where different parts of that query are extracted and named as the sort of that reusable CTE. Another reason to use common table expressions is for recursion. And what recursion is, in computer science, it means when a function calls itself. But in SQL Server, we look at recursion with CTEs is when a query calls itself. That's interesting. We can do some really interesting things there if a query can call back and call itself. It recurs many, many levels there to be able to do some interesting math and concepts with it. We can also make derived table queries much more readable by breaking them up into CTEs. Easier to test, easier to read, easier to use. And it can be, in certain cases, an alternative to a temp table or a table variable, but don't think of CTEs as a replacement for all cases of temp tables or table variables. Okay, so the syntax of using common table expressions is to use the with keyword. All CTEs start with the word with rather than select like you would normally have in your queries. It can be confusing if you're assuming that the query to select data would normally start with a select. And the scope of a CTE is confined to a single query. Now, keeping that in mind, if you create a temp table, that can be used throughout your session. If you create like a global temp table, that's something that you can use from anywhere on the SQL Server. Views can be used by many people on different sessions, but a CTE is really a single SQL statement. Once that statement is done running, everything associated with the CTE goes away. Now, in the beginning, CTEs seem just a little bit weird until you master the syntax. I remember the very first time I looked at common table expressions, I just thought, what the heck is this query doing? Well, let's take a look at the basic syntax of a CTE. You start out using the keyword of with expression name, and that expression name is the name of the CTE, and then you have the option of naming the columns that the CTE is going to return. As, and then inside of that as in the open parenthesis, close parenthesis, that's where you put a query, similar to what you would put in a subquery. That's the actual CTE query. And then you select columns from that same expression name that was in the with statement up top. Now, one of the things you'll notice that's different here is that I put a semicolon at the very beginning of this. And one of the things with CTEs is that if you're running them in a batch with other statements, the previous statement has to be terminated with a semicolon. Now, normally you don't have to terminate all your SQL statements with a semicolon, but in order for CTEs to work, the statement before has to be terminated with a semicolon. So just to be safe, I always got in the habit of putting a semicolon at the beginning, and that way if somebody forgets to terminate the statement before, it doesn't break things. So let's take a look at how to write a simple CTE query. So what I have is a test database here that I've set up called CTE Demo, and in that I've got a couple tables. One's called Royalty that has a bunch of the British royal family, and it has some numbers in there that identifies who their mother and fathers are. And then we have a table called Departments, which is departments from like an outdoor store that has camping and cycling and snow sports. And it's a hierarchy here in that you can see that some of the departments have a parent. So under the Department of Camping, with an ID of 1, here's the ID of 1 that references tents, backpack, sleeping bag, and cooking are all part of the camping department. We'll just take a look at what we have in the departments table. Select star from departments, and there are 17 departments listed there. Some of them have a parent listed, and some of them are top-level departments that don't have a parent. Then we'll take a look at what's in the royalty table, which we'll use a little bit later, but in here we have a number of British royal family and who their mother and fathers were through the sort of family tree structure. Okay, so let's first start by taking a look at a derived table. Now, what a derived table is often referred to as a subquery. So we're starting out with a select statement, and inside of that select statement, instead of selecting directly from a table, we're selecting from a subquery that references a table. This subquery is referenced as an alias of just DEPT for department, and then we're selecting from that. That's really useful when you want to do other things or calculations on the data that's coming back. Bit silly the way it's represented here because it doesn't really give any value beyond selecting what's on the inside, but it's sort of building the foundation for what we're going to do here with a CTE. So the common table expression equivalent of what this select statement does is shown here, where we have with a semicolon in front of it, just to be safe, department CTE. We call out the columns that are going to be returned, and that is optional, those columns, as, and then we have inside of parentheses our query that's the CTE query, and then we select from that department CTE. And when we run this, we get similar results to what we saw in the derived table query above. So what happens if we don't have that semicolon at the beginning of the CTE? Here's an example that shows multiple statements. Select star from departments, and then there's no terminating semicolon on that, and then it leads right into the CTE with the with statement. When we run that, we get an error message that's incorrect syntax near department CTE. And then recently, Microsoft in the newer versions of SQL Server has updated the error messaging, and they've said if this is intended to be a common table expression, you need to explicitly terminate the previous statement with a semicolon. Well, it used to be on older versions of SQL Server that it simply said syntax error without all this extra detail that makes it easy to see what's going on there. So just a reminder, keep in mind if the CTE is not the first statement in the batch, it must be preceded with a semicolon, either at the beginning of the CTE or at the end of the previous statement. Now let's take a look at some more complex examples of how to use a CTE instead of a derived table. Now to use a CTE instead of a derived table, it's great to simplify the query, and it allows for a lot cleaner code. And it does not change the performance of things at all. If you have a speedy query that's being run as a derived table, it's going to be speedy when we run it as a CTE. If you have a really slow performance issue query that's run as a derived table, it's going to run just as slow as a CTE. There's no magic happening there that's going to either improve or decrease the performance in any way. When we get to larger queries where you've got lots and lots of derived tables or subqueries, the CTEs can add a lot more value there in making it easier to read. And we'll take a look at some examples of that. It can also eliminate accidents by duplicating a derived table queries in the SQL code. I've seen queries where you might have the same subquery or derived table duplicated 2 or 3 times, and then somebody comes back later and changes the code and forgets to change one of them, and things don't work quite right. By wrapping that as a CTE, kind of like if you wrapped it with a view, it's only in one place and you don't have the issue of having to duplicate code that needs to be patched. So here's an example of a derived table without a CTE, where the parts shown in red are 2 derived tables that are aliased as Q1 and Q2, and they're being used inside of a join statement, selecting from one, doing an inner join to the other. Just a pretty simple query there. But to convert that to a CTE, the way we would do it, find the first occurrence of the derived table, create a name for it, and add CTE to the name. Now, this is one of those things that there's some debate out there over whether you should put CTE in the name of your CTE results or not. And I'm not a big fan of like naming views view underscore or procedures proc underscore, because I think that's silly. But the difference is those are things that are kept around permanently. Where a CTE, oftentimes I'm going to tack the word CTE on the end of it, or the letter CTE on the end of it, so that I don't have a conflict or that I end up stomping on a table name somewhere. I copy the derived table definition, that's just what's inside of the subquery, including the parentheses, and leave the new names as the placeholder. I then paste the query copied earlier above the select statement, and then at the top of the query add the CTE declaration using the same name from step 1, and then find all the occurrences of the same derived table query and replace them with a CTE name. And then clean up the formatting, make it look nice, and test the query. And then you end up with something like this, where the part that's shown in red is only written once, but the part in blue that's shown down below is referenced multiple times, accessing the same data. Hi, I'm Steve, and I wanted to share with you one of our services, Emergency Help. This is one of those things that if you're having a problem right now and you need someone to help you, you can call me up, make sure I'm available, and I can jump in and help. Prepay through the website, and we get things going. Make sure you give me a call to make sure I'm available before prepaying for that emergency help. But we do this a lot with customers when they're having a problem. I helped someone the other day where they said they'd been working on an issue for 3 days, and were able to get their problem resolved in just about an hour and a half. Customer was very happy. Let's take a look at a demo of how to do a similar thing to that. CTEs instead of a derived table. So here's an example of the derived table where we have a subquery here that ends up being the derived table, and another subquery here that's being interjoined to. They happen to be the exact same query. And when we run it, we're getting a list of all the top-level departments joined to all their sub-departments. So let's take a look at how do we convert that into a CTE. Get these both so we can see them here. So we start by taking that subquery, that derived table like this, and we paste it in above the query with the parentheses, just like it's done here. We then, everywhere that was referenced in the table, we give it a name. Here I'm going to call it Department CTE, and then we add the CTE declaration at the top with Department CTE with these columns as, and then we highlight it and we run the table, run the query, and I'm going to run both of them here together. And when we run both of them, you can see that we get the same result sets between the CTE and the derived table version of things. Okay, so that's not exactly rocket science at this point, and it doesn't really make a huge difference there. But we're using a very simple example here. Where it gets interesting is when those queries are much more complicated than what we're looking at here. A few notes to think about here regarding a CTE instead of a derived table, kind of summarizing a few things. Most derived tables can be very easily converted to a CTE, just like we did in that example. You can seriously reduce the amount of copy and paste errors by using a CTE if you're in the case of having multiple references of that, in that you only have the code referenced in one place rather than two copies of the same subquery. Using the CTE does not change the performance at all over a similar query written with derived tables. They perform exactly the same. For a CTE that is referenced multiple times, that CTE query is not reused. It is executed multiple times. So just like in the derived table example, where if you had two subqueries, they each got run once, in the CTE example, two references to the CTE means that same CTE is going to get run multiple times. Now that we've covered how to build a CTE and how to replace some derived tables or subqueries with CTEs, now we're going to look at how do we put multiple common table expressions into a query. So basically, you just have to build multiple CTEs and comma separate them in a single query. Here's an example of your first CTE, where you have the with and then the name and then a query inside of parentheses. And then you put a comma in a second CTE name. You don't need the word with again, you just have the CTE name, the as, and then the second query inside of parentheses. And this query does not have to be related to the first query in any way. It can have totally different tables, totally different columns, just like two different derived table queries would be. And then you can select from one CTE and interjoin to the second CTE on some value that you would join on, or cross join, or those type of things. So really all you do is you add a comma at the end of the first CTE. After the comma on the next line, declare the name. After the name, add the optional columns if you want them. Then add the as keyword, and followed by opening and closing parentheses. Then inside the parentheses, add the new CTE query, and then call the CTE query from the outer select statement. What's interesting on that last statement is that you don't actually have to call the CTE from anywhere if you're just testing, and you can comment out references to different CTEs without commenting out the whole CTE, and that CTE query won't get executed in your testing. All right, so here's an example of a simple CTE that just does a union to return a list that says John, Mary, and Bill. And then we have a second one that's last names that just returns Smith, Gibb, and Jones. And then we use cross join, and what it does is it combines all the first names with all the last names and makes up a list of 3 first names combined with all 3 last names, or 9 total names. John Smith, Mary Smith, Bill Smith, John Gibb, Mary Gibb, Bill Gibb, and John Jones, Mary Jones, and Bill Jones. That's useful if you need to populate a database with a whole bunch of test data, for instance, for load testing or performance testing. All right, let's take a look at the demo code for this. Here's an example of an inner query. We're just going to run that inner query and see what it returns. Select ID, department, and parent from departments where the department ID equals 4. We run that. Department 4 is fitness, and this is an example of how to do things without the CTE. And then we'll run that second one where we select ID, department, and parent from departments. That returns everything, and then we're joining on the ID of 1 equals the parent on 2, but since Q1 was only filtered to fitness, it's going to just return the fitness department with all the fitness subdepartments. Let's take a look at how do we do that with a CTE. Well, similar, we start out with the inner query, select ID department and parent from departments where the ID equals 4. That gives us fitness. Then we can select the ID department and parent from departments. We'll just test that piece. That gives us the whole list. And then we do the same inner join, and we can join the two of them together, and we get the top level of fitness with all the subdepartments of yoga, running, swimming listed there as well. Let's take a look at the names example that we saw from the slide we saw a minute ago. Here we're going to select John, Mary, and Bill using union statements to just build us a list of 3 first names. Now imagine if you'd done that with 20 first names instead of just 3. And then what we're going to do is we're going to wrap that in a CTE where we're just selecting the names out. Bill, John, and Mary. Not that exciting yet. What we're then going to then do is declare the F names for first names, CTE, as John, Mary, and Bill. We're going to declare the last names as Smith, Gibb, and Jones. And then we're going to select the first name and the last name, and we're going to cross-join, and that should create the 9 names that I talked about on the slide. And there you have Bill Gibb, John Gibb, Mary Gibb, Bill Jones, John Jones, Mary Jones, and Bill Smith, John Smith, Mary Smith. Now, if you want to make it more interesting, we can throw in some middle names and reformat things a little bit. So the F names is the same, the L names is the same, and the M initials has been added as another CTE where we just added a comma, gave it the name, declared the column, and put a query in, and then we reference that down here. And what that's going to do is take the 9 names that we had and give them all middle initials of A, B, or C, and take that 9 to 27 rows. And you can see there's the 27 rows. So there's this thing called a row constructor. And this was added in SQL 2008, but it's a way of saying select X from, and you give it a list of values around f of X or a function like this that creates it as a row. So what we're going to do is select X from that list, and that gives us John, Mary, and Bill. And we're going to do the same thing. Instead of using a union statement, we're going to use the row constructor to say grab these first names, grab these last names, and then cross-join. So that's just a little bit cleaner way of doing it with a CTE to come up with the same list of names we saw above. Using the same row constructor method, we can do the same thing with first, middle, and last. And we get first name, middle, initial, and last for, again, 27 rows. Where we have the initial CTE is just declared as with F names. We have the second one with a comma and then M initials. We have the third one with a comma and then L names. And then we're selecting all those first name, middle initial, last name from F names, L names, M initials, cross-joined. Doing multiple CTEs, I mean, you can put these together with a number of them. I've done a few dozen in some more complicated queries that probably should have been refactored in some way. Yeah, you can have quite a few CTEs combined into one big query if needed. So next, if you've got multiple CTEs, we can do what are considered nested CTEs, where the previous multiples we looked at, it was just 2 CTEs that were being, or 3 CTEs that were being referenced from the outer query. To nest it, it's like the Russian dolls that are pronounced matryoshkis, where you have one that's inside of another, that's inside of another, that's inside of another, and so on. And basically, a nested CTE query is one that it calls a previous CTE that's been declared in the list. And it can only reference itself or queries declared earlier in the query. You can't reference a CTE that's further down in the list. Here's an example. We just have a real simple query where we're simply selecting 1 as a number. We then have a second CTE that references, or this is CTE 1 referencing CTE 0, where it just grabs the number plus 1. And then CTE 2 references CTE 1, which adds another number to it. And then if we say select star from CTE 2, what's that going to give us? Select star from CTE 2 is going to select the number from CTE 1 and add 1 to it, but CTE 1 is going to select the number from CTE 0 and add 1 to it. CTE 0 just returns 1, so the output on this is going to be 3. Let's take a look at some examples there. Here's the one we just looked at, and if we wanted to test this as we go, we could say select star from CTE 0. And we could run that and confirm that CTE 0 simply returns the number 1. Then we could slide this down and say select from CTE 1 and confirm that, yep, that does return 2. It references CTE 0, and then that starts with 1 and adds another 1 to it. And then select star from CTE 2 at the end returns the number 3. So these are nested. If we wanted to do something like, say, CTE 1 was going to select from CTE 2, It's not going to let us do that because CTE2, you can already see the squiggly lines underneath it that say it's invalid. It doesn't exist at the time until after CTE1 has been run. So next I want to take a look at a CTE here that is a little bit more complicated, but a little bit more real world than what we're looking at with some of the examples above. And what we've got here is a CTE called unused CTEs. And when we run it, it goes and looks up any unused indexes, which doesn't return any because we don't have them yet in the demo. So this is this little test database. So what I'm going to do is I'm going to create 3 indexes here so it'll show up in the list on the table departments. And they're kind of bad practice to create 3 indexes that have the exact same column definitions, but it's for an example, so we'll just go with it. And what we're going to do is say select from all the unused indexes, and it shows that there's 2 that are unused. We have this other one that is index CTE that selects all of the indexes, and then it's going to go and look for duplicate indexes. And what this is going to do is it's going to grab the table name columns and whatnot from, selecting from tables, getting index columns and so on. That's not going to work, I just realized as I say that, because we've got it referencing index CTE, which is up above. So the way we want to test just that dupe index as CTE is we could uncomment that, highlight up through the top of where the CTE starts, and when we run it, we can see that there's a table name called departments that has duplicates on the ID and parent columns. But if we replace the dupe index as CTE, we're selecting from the unused CTE and the dupe index as CTE, and we're just joining those into 2 columns that will return the number of indexes and the number of duplicate indexes. Kind of cleaning that query up into one query. You could easily run this as multiple queries the way we're using it here, but it depends on how you want your code to look. So here it gives us a table that shows us for this database there are 2 unused indexes and 1 duplicate index shown there. Next, we're going to move on to data paging with a common table expression. Basically what data paging is when you've got a large result set, and what you want to do is display like the top 20 or top 50 results. So if you go to any search engine and do a search on some topic, you'll see that you'll get like the top 20 results out of 2 million or 200,000 or a few hundred. What data paging allows you to do is to page through and see those results. Now, I've seen this done on different website projects really poorly a lot of times, where somebody will just say select star from a table where the result set matches your search criteria, and the query ends up iterating over like a few thousand or 100,000 rows and only displaying the ones that are needed in the web page, like getting the top 20 and then getting like 21 through 40 and 41 through 60. But each time it's doing a whole lot of work there, and so many times I've seen where this doesn't scale, where it works great in a dev environment where there's only a few hundred rows, but then as soon as it gets into reality, things really bog down. And you can really simplify this with CTEs. There's a great way to kind of using calculations there, figure out what page you are based off of page sizing and just display the data that you need for that given page without as much work. SQL Server 2012, the offset and fetch keywords were introduced, which is a little bit easier to use than a CTE for data paging and a little bit more efficient, but it doesn't always work in all environments. So we're going to take a look at both ways of doing this to make sure that you understand the pros and cons around both of them. So here's an example of data paging. This is selecting from tables and indexes that are in the database, and it starts out where page 1 has rows 1 through 10. Page 2 has rows 11 through 20. Page 3 has rows 21 through 30. And you can do this just by selecting top 10, top 20, top 30, but you'll find out that the further you go into the pages, the slower that it gets. So here's an example where the blue query, so here's an example of a CTE that's been created for data paging, where the select statement inside of the CTE that's shown in blue is just grabbing some table names and column names from the sys.columns table, and there's a lot of them in there. And then what it's doing is it's calculating the row number ordered by something, and it's ordering by the object name. So it's the alphabetical listing as the row. And normally without a CTE, you cannot use the row number function in a where clause or a having type clause to filter things out. It needs to be done, and actually, you can't even use it in a subquery and if you're going to use it for filtering that way. So this is one of those things that wrapping it in a CTE, this is one of those things where wrapping it in a CTE makes it so you can filter on it later, and then we're going to select from the CTE where the row is between a specific page number times the page size. So let's take a look at that demo. So we're going to be back in that same CTE demo database. We're just going to select from the sys.columns table, which is one of the SQL system tables if you're not familiar with it, and it just shows, in this example, sorted by table name, all of the tables and what all of their columns are. So what we're going to look at is how to put that into a paging CTE. So this is very similar to what we showed on the slide a moment ago, but we've declared some variables here where we have a page number and a page size. And for this example, I want to get to page 2 with page sizing of 10. Inside here, we're going to do a select of the table name and the column names and a row number, and it'll look like this. But we can't use that row number in the where clause inside of the CTE. So what we have to do is we use it in the where clause outside of the CTE. We highlight the whole query, and there we get rows 11 through 20. If we change this to, let's say, page 4 with page size of being 15 rows, when we run the query, that should give us row 46 through 60 as we're seeing there. But that's something that would be a little bit easier if we could wrap it in a procedure. So let's take a look at putting that into a procedure. We're just going to call it tables and column pager, where it's just going to take a page size and a page number. We're going to create the procedure with the same query that we used just above there, but instead of declaring the variables inside, we're going to pass them in as parameters. Create the procedure, and then we're going to say, give me tables and columns for page 1, 2, and 3, and we'll get 3 result sets. And the first result set is row 1 through 10. The second result set is 11 through 18. And the third one is rows 21 through 30. And when we look down here, that comes from doing this. If we went in and say, okay, give me the 5th page, there's page 5, which is rows 41 through 50. So that's one way of doing it. Another way, and yeah, when CTEs were first introduced, that was really the primary way of doing really good data paging. And a lot of people, I think, picked up CTEs purely to be able to do that kind of data paging. But with SQL Server 2012 and newer, there's this new option where we can use the offset command. And we're going to do the same query here, offset page number times page size, which would be, if page number was 2, would be an offset of 2 minus 1 would be 1 times the page size of 10 and give me 10 rows. So what I'm going to do is run these side by side, the original CTE and the page number here, and compare the results. And you can see we're getting the exact same results there. But the advantage of the CTE is we can display the page number as it was shown prior to the filtering here. Let's take a look at how these actually perform. So I'm just going to turn on statistics IO and time, and I'm going to hit Control M. Actually, I'm just going to do Control M to turn on the actual execution plan and look at the comparison here. We run these two, and you can see comparing them, 55% of the cost was associated with the CTE, and 45% of the cost was associated with the rows. With the offset and rows options. Now, that's one of those things that performance, as usual, may vary, and there may be situations where the CTE is a better option, and there may be situations where the offset and rows is the best option. It really depends on how it performs and the specific data behind it. So if you're looking at doing paging, you might want to compare the two of those and see which works best. So here's just an example showing the alternative to the CTE using the offset and fetch like we just looked at, if you're using SQL Server 2012 or newer, which hopefully in today's day and age most people are. Now on to CTEs in stored procedures, functions, and views. When I first started doing this presentation several years ago, people would ask, oh, can the CTE be used in a function or can it be used in a view? And the answer to that is yes. And as we saw above, we actually already put the CTE into a procedure, so we know that that works. So let's just create a procedure here that's called show departments. And inside of that, we're going to have the department CTE that just runs a query and displays the results. And once that procedure is created, we're going to run it, and what we get back is just a list from that query. So no problem. CTEs work great in stored procedures. How about in an inline table-valued function? That's where it's a SQL Server function that only has a single statement, and it returns a table. So what we've got is we're going to create the function. Okay, so what we're going to do is we're going to create the function. In there, it's the same CTE we've been looking at before, and we're going to do that, and we're going to compile that. And then to use it, we just say select star from the function name, and then with parentheses after it. And there we go, just a different way of getting access to that same CTE. And then we can also put them in multi-statement functions, although you run into different issues performance-wise around multi-statement, but we're going to have two different CTEs in there that are both inserting into the result set that is the return value from the multi-valued function. And then when we run it, there we go, we get the results from both of the queries that were shown up above, where the parent equals 1 and the parent equals 3, which is camping and snow sports. All right, how about in a scalar function, a function that does not return a result set? Well, the difference with this is, yes, we can use the CTE in there, but we have to assign the results into a return value rather than just displaying it as a result set. Let's take a look. When we compile that, we select, and we're not selecting star from, we're actually just selecting the function name. And when we run that, we get back 4 as our result value that's coming from the count for the number of top-level departments. Then on to creating a view with the CTE. A lot of people ask about performance issues around views and CTEs. Well, if you've written a query that's going to perform poorly, it's going to perform poorly when it's in a view. That doesn't really change anything. If you've got a query that works great, it should work great when you're working in a view. The difference is sometimes SQL Server will get a little bit confused with filtering and things on the performance when you have nested views or multiple levels of nested views. So we kind of recommend staying away from that. But as far as putting a CTE into a view, you do it just like this. We select star from the view, and we get the same results that we've been getting all along. So that wraps up CTEs in stored procedures, functions, and views. Now on to recursive common table expressions. This is my favorite part, and this is where it gets really fun, is working with recursive CTEs. Because with recursive CTEs, we're doing things that are really difficult to do any other way with SQL Server. So a CTE is considered recursive when the CTE references itself. Well, that's interesting. You can't do that in a view where a view references itself. But in the CTE, you can actually declare the CTE and inside of that query definition, reference that same CTE itself. Now, the recursion will keep going until it hits one of the following stop criteria. One is when the query produces no results, or referencing itself and going recursively doesn't give you anything new to add into your results, or when the max recursion is hit. And the default on max recursion is 100. So if you're going 100 levels deep or less than 100 levels deep, that's a good default there. But if you have a query that you need to go more than 100 levels deep, you need to specify a different max recursion value. Now, I think the max you can specify is like 32,000 or somewhere around there, or you can specify 0, which implies no max recursion, which just says keep recursing until the query either produces no results or until the SQL Server runs out of memory, one or the other. And yes, I have run SQL Server out of memory on some pretty big systems, experimenting around with recursive CTEs. Some of the uses for recursive CTEs are hierarchical listing of categories. So we looked at our outdoor store which had snowboard sports and ski equipment and camping and all those kind of things. And we were able to display a list of categories, but we weren't able to do anything to really put that into a hierarchy of what's a subcategory of another. They're great for recursive calculations, things like a Fibonacci sequence. Really fun to do with the CTE. You can also do things like kind of a tree view of like a family tree structure or things like that, and much, much more. But from my perspective, recursive CTEs are the most interesting part of common table expressions. So let's take a look at a recursion overview. If you were assigned the task of summing the numbers from 1 to 10 without recursion, you might put something together like this, where you say 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4, 3, 2, 1 equals 55. That works great if you've got a single function or single math function you want to work with there. But then, if you wanted to say sum the numbers recursively from 1 to 10, you could say the sum of the numbers from 1 to 10 just happens to be 10 plus the sum of the numbers from 1 to 9. And then, which is 10 plus 9 plus the sum of the numbers 1 to 8. And sort of working through the logic, finally we get back to the same, almost the same layout as above, is 10 plus 9 plus 8 plus 7 plus 6, but it's easier just to declare it and say it's 10 plus the sum of numbers 1 to 9. Now, imagine if you were trying to do these sums for bigger numbers in the thousands. This would take you a whole lot of time, but doing it recursively allows you to accommodate multiple depths that you're dealing with there. So let's take a look at some of the terminology around recursion. Now, this is just a little bit different than anything else that you may see done in SQL Server. The anchor query. Every recursive CTE needs an anchor query. And what an anchor query is it defines the start of the recursion. And what the anchor query is it defines the start of the recursion. This is the part that cannot reference the CTE itself. It has to start with some base starting point. So if you're doing a hierarchy of departments, well, you're starting the recursion may be giving me the top level departments, and then the recursive part may be for every top level department, give me everything that's a department below it. And then with this, you can have one or more anchor queries. Then you've got the recursive query. This is the part that repeats, and this is the part that references the CTE itself and can repeat many, many, many levels of depth. And you can have one or more recursive queries. So for instance, if you were doing like a family tree structure, you might have select all of the people at the lowest level, and then for each of those persons you may have, so for each of those people you may have one query that selects the mother's side of the family and another query that selects the father's side of the family, and then those recursive query would run and run that for everyone in the result set, and you'd end up looking up all of the original starting people and then all of their mothers and all their fathers on both sides until there's no data to return, or until you hit the max recursion level. So max recursion, it's the number of times to repeat the recursive query depth. The default is 100, and a max recursion of 0 implies no maximum. Just keep going until there's no results or until the server runs out of memory. So here's an example of building a recursive common table expression. I'm going to start out with the with statement. We're going to call it department CTE, and we're going to label the columns that we're going to return. Department ID, the department, the parent, and those are all things we've seen before earlier in the presentation. And then we're going to be asking for the level, and the level is going to be the depth of recursion. So all the people at the top level will be level 0. So all the departments at the top level will be level 0. Then all the departments at the level below that will be level 1. And for subdepartments below that, they'll be level 2, 3, 4, or deeper, depending on how far we go. Then we add the anchor query. And this is basically just saying, give me all the departments where the parent is null, which means give me all the top level departments, and setting 0 as the level on those, just hard coding that as a starting point. Union all, that's kind of the magic keyword inside of the CTE that says, take that anchor query that's above and connect it up to the recursive query. And here the recursive query is shown in red, where we're saying, select the department ID, department, and parent from departments, but we're joining back to the department CTE, which is the CTE we're building right now, and we're joining it on the department ID, which equals the parent in departments. And then we're grabbing the level from the department CTE and adding 1 to it. And that's how we're saying that first level of recursion will be 0 plus 1, or at level 1. The second level will be 0 plus 1 plus 1, or level 2. And then the last thing we do is we just select from that CTE ordering by some value we want to order by. I wanted to share with you a bit of details on our database corruption repair service. This is something that we do regularly. If you've got a database that's corrupt, we can be there to help. We get most databases repaired in 24 to 48 hours. It starts with a free 30-minute consult or a phone call, and we can get started taking a look at what's going on and determine if we can help get your database repaired and up and running again. All right, let's take a look at the demo and see exactly how that works. So we're going to take a look at our departments table again, just like it's looked all the way through the demo. 17 departments there. Some of them have parents defined, some of them don't. And then we're going to find all the top level departments. So that's where the parent is null. And here we get 4 top level departments: camping, cycles, snow sports, and fitness. Now, a non-CTE way to do this would just be to take departments and join it to departments again on the parent. And when we run that, we'd be able to get the top level and the child level and be able to build a 2-level hierarchy there. But it gets really unwieldy when you get to the point of more than 2 levels or 3 levels there. Another way is you could do this and set the level here, similar to what we talked about in the CTE, but these are really only good when there's not a lot of depth into the departments there. So, okay, now let's take a look at building the anchor query. So here the anchor query we're going to start with is just give me all the departments that are at the top level where the parent is null. And we're going to set the level, and this was a typo I need to fix, and we're going to set the level to 0 as the starting point. So all the top level will be level 0. Then we're going to wrap that in a CTE. So we're just going to call this department CTE. We're going to put our anchor query in there, and we're going to select everything out of that. And like we talked about earlier on some of the simple CTEs, not very exciting yet. So all we're doing is we're getting the top levels. They've been defined as level 0. You could do all of that with a non-CTE type query, but here's where it's going to get interesting. Now what we need to do is to go find those that are sub-departments of the other departments. And the way we're going to do that, and this is going to be the recursive part of it, we're going to say, give me the ID, department, and parent. We're going to add 1 to the previous level from departments, and then we're going to interjoin back to the CTE itself, linking up the parent from the departments to the ID that's defined in the CTE, which would initially be the top level, or it would be the level prior to this level. But we can't run that because that department CTE doesn't exist yet. So what we do is we declare the CTE, we have the anchor query, we drop in the union all, which is how we say run this top thing first, run the anchor query first, and then for all the results that come out of that, run this next query. And for all the results that come out of that, repeatedly run this next query until there's no more results or until our recursion level is hit. So here we're going to say select star from department CTE. We get all of our departments listed and the level they're at. Okay, but let's make it more interesting. Let's run this procedure I created earlier, which fills in more departments. And when we look at the non-CTE query, that really gets thrown off here because there's all this stuff that has a parent but is not at level 0 or 1. So what we're going to do is we'll run the CTE again and take a look at it, and we can see here's all the level 0 items, here's all the level 1 items, here's all the level 2 items, which is new. This 1 person, 2 person, 3 person, and 4 person are a child of item 5. Item 5 is tents, so this is 1 person tent. And then under here we have backpacking, family camping, mountaineering, ultralight, and mountaineering, and those are a child of 19, so those are 2-person tents. And then ultra lightweight, lightweight, and standard, which are a child of department 24, which is backpacking. So this standard would be a standard backpacking 2-person tent that's in the camping department. All right, that's handy, but we're going to look at some better ways to format this in a minute. We'll come back to formatting shortly, but for now, let's take a look at another recursive CTE that's not looking at tables, but it's just looking at math. And here, we could create a recursive function that's called sum of parts and select from the sum of parts. Basically, we're creating a function that selects from itself. And what it does is it just says, give me the current number plus the sum of parts of that number minus 1. So if we say sum of parts of 10, we should get the 55 that we asked for, or the sum of parts of 3, and we get 6, because 3 plus 2 plus 1 is 6. But when we look at sum of parts of something a little bit larger, oh gee, the nesting level on stored procedures, functions, or triggers is 32. So we can only, using recursion with functions, go 32 levels deep on the recursion. Okay, so let's take a look at how to do the same thing with the CTE and get around that limitation. First, we build the anchor query. We say select one as the count number and 1 as the grand total. So the sum of parts of 1 is simply just 1, because 1 plus nothing is 1. Then what we do is we pop that into a CTE, wrap it with the CTE, and it's still just the anchor query, just counting to 1. Okay, not very exciting, because technically all of us could have done that one in our head. We don't need a database to do that. But let's take a look at the recursive query for this. We're going to say, give me the count number plus 1. That's our level we've gone to. And we're looking at the grand, so this would be, the count number would initially be 1, and then it would be 2, and then it would be 3 as it goes through there. And we're going to take the grand total plus this current count number. So this would be at 3, it would be 3 plus 4. If this was at level 3, the grand total would be the 6 from the previous level, plus the count number plus 1, which would be 3 plus 1 would be 4, and it would make it 10 for level 4. We put all that into a CTE, we declare the CTE, throw in the anchor query, we use the union all to connect it up as a recursive query. We put in the recursive parts, and then we select from it. Well, we ran into an error there. The maximum recursion of 100 has been exhausted before statement completion. Well, we did get further than we did with the recursive function, and you can see if we look here at level 10, we're getting 55. At level 11, we get 66, which is 55 plus 11. We go way down here at 100, we get 5,050, and then at 101, we've gone beyond the max recursion level, and things stop. So the way to get around this is we can add a where clause that will terminate the recursion at some level. So if we just wanted to look at up to level 10 on the sum of parts, we could use a where clause like this. And what that did, fix the layout here a little bit so we can look at it, is it said only run the recursive query until the count number is at 10. So only run it 10 times. If we change this to 20, run the CTE again, we get the sum of parts for 20 is 210. Okay, but what we were looking for in our initial math function was not a list of the sum of parts of everything up to that level. We were really looking for just the answer. So what is the sum of parts of 10? Well, in this case, we're just going to say run that whole query and give me the biggest number up to level 10, and that's the sum of parts. There we go. Sum of parts is 55 when the recursion level is 10, or the count number is less than 10. What if we wanted to go further? If we want to do the sum of parts of 150, let's try that. Same CTE. All I've done is change that 10 to 150 down here. We go and run that, and kaboom, we get an error. The statement has been terminated. The maximum recursion of 100 has been exhausted before statement completion. Okay, the way we're going to get around that is we're going to put in this parameter called option max recursion. And I'm just going to throw in 200 as a number. I could have technically put in 151 as being slightly larger than what I'm looking for here, but I'm just going to throw in 200. You could go with something bigger like 1,000 and it would work fine. And when we run that, we get the sum of parts for 150, which is 11,325. Okay, well, one of the things I like to do is performance and pushing things to their limit. So what I want to do next is see how far can we push this sum of parts. Can we do the sum of parts for 40,000 with the option of max recursion equaling 40,000? No, we cannot do that because the value of 40,000 specified exceeds the limit of 32,767. Okay, well, the way we can get around that, and this is the dangerous way of doing it, and we'll just copy that original line and comment it out. We say option max recursion of 0. 0 means go indefinitely. We run that, and now the sum of parts of 40,000 is this big number here with lots and lots of zeros after it. The recursion on that went 40,000 levels deep, and it stopped. So how can we prove that? Well, if we just say select star and comment out the max, we run that same query. Our result set, you can see down in the bottom corner here, is 40,000 rows, and we scroll all down to the bottom, and there's 40,000 rows that were taken out of that recursive query. All right, continuing on, let's take a look at another table, and we're going to do some recursion here. We have this royalty table, and this is just looking up some of the British royal family. Disclaimer, I'm not related to any of them. And then we're going to look on each one. Some of them have their mother and father defined, and some of them don't, depending on how far back. Like anyone's family tree, you eventually go far enough back and you don't have who the mother and father are. So if we look down here, we have Queen Elizabeth II of Windsor. Her mother is ID of 6 and her father is ID of 3. So here's ID of 6, which is Elizabeth Angela Marguerite Bowen Lyon. And here's 3, which is her father, which is George VI, Windsor King of England, if I'm doing my Roman numerals correctly. But this isn't really a very good way to show a family tree. It's hard to follow. So what we're going to do is we're going to build a royal family tree with a CTE. We're going to use the anchor query, and we're just going to start with ID of 17, because that happens to be William Arthur Philip Windsor, or Prince William, as I believe he's known as. We're going to use that as our anchor query. That's our starting point. And then we're going to say, give me, for this individual, ID of 17, on the recursive query, give me his mother and all of his mother's mothers. And when we select from this recursive CTE, we now see Prince William, his mother is 16. 16 is Diana Frances, or Lady Di, which her mother is 18, which is Frances Ruth Burke Roche. Hopefully I'm pronouncing all those correctly. If I'm not, it doesn't matter for the recursion part. But we don't have the father side showing up very well here. So what we're going to take a look at next is if we took that same query above and we simply replace the join of the mother to replace it with the father, we run this. Here's Prince William, his father, Prince Charles, his father, Philip, Duke of Edinburgh, Andreas, Prince of Greece, and William George I of Helens. Again, not sure if I'm pronouncing those correctly. So we were able to track on the father's side back. So this is like a left-handed family tree and a right-handed family tree, going back on one side or the other, but we're not going back on both sides. So how do we go back on both sides? Well, what we do is we take that same CTE, and here the part that's highlighted is the exact part above that was showing the father. We throw in a second recursive query with another union all that says for everybody returned from all of these results, we want to also look at who the mother is. And we're going to grab that from the royal tree CTE. And that's kind of like saying select star from the original table, because it gave us everybody back, but it was able to give the relationships there. We're going to do a few other things, but we're going to come back to the royal tree family CTE there in a few minutes with some better layout. But to start with, let's take a look at a little bit more recursion here, and then we'll come back and take a look at some of the other, some of them above in a moment. So here we're going to use the Fibonacci sequence. And if you're not familiar with the Fibonacci sequence is basically the numbers 0 and 1, and then each subsequent number, and I need to put a little carriage return in here so we can see. Each subsequent number is the sum of the previous two. So 0 and 1 is 1, so then the Fibonacci sequence there would be 1. 1 and 1 is 2. 1 and 2 is 3. 2 and 3 is 5. 3 and 5 is 8, and so on. But it gets a little bit hard to follow in there, so let's take a look at how to do this. So we build the initial Fibonacci sequence as just select 0 and 1, because by definition, the Fibonacci sequence starts with 0 and 1. So there's the initial Fibonacci sequence, 0 and 1, and the total value is 1. But now what we're going to do is we're going to say select 0 and 1, and then give me n plus the previous value plus n as the Fibonacci number, where n is less than this ginormous number right there. So we can see the Fibonacci sequence goes like this. 0, 1, 1, 2, 3, which is 2 plus 1, 5, which is 3 plus 2, 8, which is 5 plus 3 above it, 13, which is the 2 above, 21, which is the 2 above, 34, which is the 2 above, and then things start getting big really fast. And next thing you know, we're down into some really big numbers down here when it's taking this value and that value and adding them up to the next one. But there you go, Fibonacci sequence calculated using a common table expression. We can clean it up a little bit by in the output just displaying the number we want rather than 2 columns. That's pretty straightforward there. And again, we're using the max recursion of 0 just to be safe there. or maybe not to be safe, maybe to be a little bit risky because you never know when it's going to run out. So then what we're going to do is try building the Fibonacci sequence out into a string of text. And let's take a look at what that looks like. So here we have the Fibonacci sequence basically pivoted or kind of turned around as a single string. And I'm just going to copy this value and paste it into a new window. And you can see the Fibonacci sequence gets pretty big quickly there. But we've got the entire sequence put out as a varchar value rather than as a numeric value, showing the entire sequence. Again, just using some fun math here to kind of show off how specific things work with recursion. Okay, let's take a look at factorial next. Calculating factorials with a CTE. Well, the way factorial works, and a factorial is represented as an exclamation point. Factorial works if 5 factorial is 5 times 4 times 3 times 2 times 1, which gives a value of 120. Okay, that's not recursive, and let's just start building an anchor query. So factorial of 1 is simple. It's 1 times all the numbers less than 1 and greater than 0, which is just 1. So we select the n and the factorial, and we get the number is 1 and the factorial is 1. Anchor queries are usually boring. That's okay. But what we're going to do now is take that anchor query and build it into a recursive query. So here we have the declaration of the CTE, the anchor query, the union all, and then we're going to say for factorial, we're going to grab n plus 1 to each level deep, we're going to add 1 to it, and then we're going to take that n plus 1 value times the previous factorial. So at level 2, it would be 2 times 1, or 2. At level 3, it would be 3 times 2, or 6, and so on. We select that from factorial, and we're going to abort when we get to 5 levels deep, because we don't want this to run wild and hit our recursion level. So let's run this, and we can see that factorial of 1 is 1, factorial of 2 is 2, factorial of 3 is 6, factorial of 4 is 24, and 5 is 120. Let's push it a little bit further and see what happens. Let's look for a factorial of 20. So all I've really done is just change the 5 above to a 20 as it's shown here. We run it, and we get an arithmetic overflow converting expressions to data type int. Well, the data type int only holds so big. So large of a piece of data. So it's about 4 billion-ish, if I remember the number off the top of my head. So what we're doing there is we're getting a point to where it exceeds what can be held in an int. So what we can do to fix that and get around that is we simply cast our starting value as a big int, and then everything in that column from levels on down will be a big int, which will allow for larger numbers. And you can see now we get to a factorial level of 20. Well beyond that 4 billion limit we're hitting with a really, really big number here. But how far can we go? Well, if we change this 20 to, let's say, 30, can we accommodate that? Well, even a big int overflows at a factorial of 30, and in fact, 20 was all we got to. 21 was where it overflowed. But I really want to calculate a higher factorial number, so what I'm going to do is I'm going to cast that initial starting number as a numeric 38 rather than a big int, which should let us go larger than what the big int would hold. We run that, our factorial calculation, as you can see below, gets really big fast, and there we go. The factorial of 33 is this gigantic number you can see there. If we try going to 34, well, I think at this point that's where we overflow the numeric value. Yep, same issue. So we hit the limits of the data types pretty darn quick when we're doing things like factorial. Okay, so now we're going to come back to the royal tree CTE that we're looking at. And here's the same query we looked at earlier, where we're selecting the mother and the father on both sides of the tree for number 17, which is Prince William. And there it is, but that's kind of hard to follow. So let's see if we can figure out how to better represent it. So what we're going to do is we're going to tag this top level person as a source. Everybody on the father side, we're going to put the word father there for relationship, and everyone on the mother side, we're going to use the word mother. Now at least we can see that here is the starting person, and then everyone below that is laid out as who's a father or a mother, but it's not really clear. Like if I was looking at this as a family tree, it'd be really hard to follow. But we at least know who all the fathers and mothers are. But next, what I want to do is I want to add a new column, and I'm going to call that tree path. And what tree path is it's going to be a tool that we're going to use to kind of indent and lay things out a little bit so we can get a better understanding of the data. So initially, we're just going to cast the name as a tree path, and then we're going to take the previous tree path, and on the father's side, we tack on this little arrow and father, and we put the father's name. And on the mother's side, we tack on a little arrow and mother, and we put the mother's name. And we're only going to go 3 levels deep, so this is a little bit easier to follow and take a look at. And looking here, because things get wide real quick, we can see at any level the relationship between Prince William is that his mother is Lady Di, and her mother is Frances Ruth Burke. Or if we want to look at the relationship between Prince William and Elizabeth II, it's Prince William, his father is Prince Charles, and then the mother is Queen Elizabeth II. Visualizing the data in the CTE can be as valuable as just being able to calculate it. To me, this is far more valuable than what we were looking at above, where it just showed the list of who's who and who their parents are. All right, so let's take a look at doing this a different way. What we're doing now, and I wanted to bring up the results while we look at the query so that you can see them both at the same time, is that with our anchor query, we're grabbing ID of 17, which is Prince William, and we're just declaring that he is the root value in the tree root. So here's the root, and then what we're going to do, as we do each level of recursion, we're going to use the previous tree path. So based off the recursion, we're going to tag each one as a father or the mother, and then down in the results, we're going to use this replicate function, and we're basically going to say replicate a period and some spaces level number of times. So at the root level, which is level 0, we don't get that anytime, and from there on down, we indent based off of the level, and then we order by the tree path, and that ends up giving us the structure here, where the tree path is what we saw in the previous query with the full name list. Here we're getting indentation that shows at the root. It's real quick to see Prince William's at the root. Here's his father, here's his mother, and then for Lady Di, here's her mother and father. For Prince Charles, here's his father, Philip and Elizabeth. And for Elizabeth, her father is George and Elizabeth. George VI, his father is George V, and Mary, Princess of Teck. There we go. Much better formatting out of Recursive CTE. This is the fun stuff. All right, that wraps up the demo on Recursive CTEs. A few notes and things to remember with Recursive CTEs. The recursion stops when the recursion produces no results or when max recursion is hit. You can use T-SQL functions to do recursions as well, but that only will go 32 levels deep. When using recursion, if you're specifying max recursion, you can go 32,767 levels deep, but if you need to do recursion beyond that, you can use the max recursion setting of 0, which says go until the recursion stops or until you run out of memory. And I have confirmed up to 100 million levels of recursion. I had a pretty big test server that I was kind of building out, and while I was testing it, I thought, let's just try a big query here and see what happens. And I was able to get 100 million levels of recursion before we ran that thing out of memory. There's a lot of bonus material available, and you can get this at stevestedman.com. There are a whole lot of different CTE queries, and if you download the examples for the presentation, there's even more beyond what we looked at in this presentation. More information you can get, our company page is stedmansolutions.com. If you need any help with query tuning work, SQL Server performance assessments, corruption repair, or just some SQL mentoring help, we can help with that at stedmansolutions.com. You can visit my blog where this will be posted with additional demo material at stevestedman.com, or you can send me an email, steve@stedmansolutions.com, and all the slides and sample SQL are available for download at stevestedman.com. Thanks for joining me today. That wraps up the presentation. Oh, but wait, we have some bonus material. Here's some questions I want to take a look at. There's a lot of sort of myths and misunderstanding out there with common table expressions. So as we go through this, make your best guess on each one of these and see how things go. So CTE executions. So as a named result set, the CTE is only run once, even if it's referenced multiple times in a query. Is that true or is that false? That is false. The CTE is executed once for each time that it is referenced in a query. Example here where we have the CTE of department CTE being referenced on a self-join. that inner query in the dark red will be run twice. CTEs are proprietary, meaning they're only a Microsoft SQL Server thing. Is this true or false? We're going to have to guess at this one because I don't think we talked about this. Common table expressions are supported by several major database platforms, including the PostgreSQL, DB2, Oracle, and of course SQL Server, and it is defined in the SQL 99 spec. However, as usually happens, they are slightly different, same concept, but slightly different syntax here and there as on the different platforms. CTEs and hierarchical queries. CTEs are a great way to create recursive hierarchical queries. True or false? True. Recursive hierarchical queries are easy to write with a CTE, and CTEs save time, are easier to follow, and work great for hierarchical data. SQL Server only supports CTEs on SQL Server Enterprise Edition 2008 R2 or newer. True or false? False. Common table expressions have been supported since SQL Server 2005 and are available in all versions: Standard, Express, Enterprise, Developer, and even Azure SQL. CTEs can be defined in user-defined routines such as functions, stored procedures, triggers, and views. True or false? True. Common table expressions can be defined and used inside of all of those items. CTEs and nesting. CTEs can be nested, and one CTE can reference an earlier CTE. True or false? True. Common table expressions can be nested. Just define multiple CTEs and reference an earlier CTE from the later one. Indexing in CTEs. Indexes can be added to CTEs to boost performance. True or false? Well, this one is false, and the reason is you cannot apply an index because it's not really a thing that stays around like a table. It's only a temporary deal, and you cannot add an index to a CTE. However, if there is something that you really need to index the results from, you can always insert the output from the CTE into a table or a temp table, and then add indexes at that point. A view or a CTE, which performs better? A non-recursive CTE or a view? They're the same. The big gain is the recursive CTE, which you can't achieve with a view. CTEs are a great way to do data paging for a result grid. True or false? Well, in the lingo of any great DBA, it depends. From SQL Server 2012 and newer, the offset and fetch clause on select statements makes it a little bit easier, and it performs a little bit better in some test environments. But for 2005, 2008, and 2008 R2, CTE is definitely the best option.